Welcome to The Explainer. Today, we're going to decode the physical properties of aldehydes and ketones. You know, they're the molecules behind so many everyday scents and flavors. All right, let's dive right in.
So everything we're about to talk about, boiling points, solubility, you name it, it all hinges on one single feature that all aldehydes and ketones share, and that's the carbonyl group. This is where all the magic happens.
I want you to think of that double bond between the carbon and the oxygen atom as a constant microscopic tug-of-war over electrons. And in this battle, well, the super electronegative oxygen atom is the undisputed champion. It yanks those shared electrons way closer to itself.
So because of this uneven sharing, you get a permanent separation of charge. The oxygen end becomes just a little bit negative, we show that with a delta minus symbol, and the carbon end becomes a little bit positive, or delta plus. This imbalance is called polarity, and it makes the molecule a dipole. Honestly, this is the key that unlocks everything else we're going to talk about.
Okay, so we've got this tiny, invisible imbalance of power at the molecular level. Big deal, right? Well, it is a huge deal. Let's see how it creates these massive, real-world consequences that we can actually see and measure.
Since every molecule has a positive and a negative end, they start attracting each other, kind of like tiny little magnets. You know, the positive end of one molecule is drawn to the negative end of its neighbor. These forces are called dipole-dipole interactions, and as you can see, they influence everything from whether something's a liquid or a gas, all the way to its scent.
And this slide just shows it perfectly, how size changes the whole game. The smallest aldehyde, methanol, it's a really pungent gas at room temperature. But as you start adding more carbon atoms, the molecules get bigger, and those attractive forces get stronger, so they become liquids and then solids, and their scents totally transform. They become these fragrant notes that are absolutely essential to the perfume industry. Okay, now let's zero in on one of the most important properties dictated by these forces, the boiling point. It turns out that when we compare molecules of a similar size, aldehydes and ketones fit into a very specific and totally predictable hierarchy.
Think of it like a league table of forces. Down at the bottom, in what we're calling Tier 1, you've got your hydrocarbons and ethers. They're held together by the weakest forces, called van der Waals forces. Then, way up at the top in Tier 3 are alcohols, with super powerful hydrogen bonds. And where do our aldehydes and ketones land? Right in the sweet spot in the middle. Their dipole-dipole interactions are definitely stronger than van der Waals forces, but they're not quite as strong as hydrogen bonds.
And here's the hard data to prove it. Just look at these 5 molecules. They all have almost the exact same mass. But their boiling points, they are worlds apart. Check out N-butane, the alkane. It boils at just 273 Kelvin. But then propan-1-ol, the alcohol, boils way, way up at 370 Kelvin. And right in the middle, just like we predicted, are our aldehyde and ketone. It's a perfect confirmation of the hierarchy.
All right, let's switch gears and move on to solubility. We're going to see how the carbonyl group's split personality, that polar head, decides whether it's going to dissolve in a polar solvent like water.
So that polar carbonyl group, it acts like a water-loving head. Its partially negative oxygen atom is really attractive to the partially positive hydrogen atoms in water molecules. And this is cool. It allows it to form hydrogen bonds with water, even though it can't form them with other molecules of itself. That's why the smaller members, like propanone, can mix freely with water in pretty much any proportion.
But, and this is a big but, there's a catch. The rest of the molecule is a chain of carbon and hydrogen, and that part is nonpolar and water-fearing, or hydrophobic. As this carbon chain tail gets longer and longer, it starts to take over. It basically acts like this big, oily barrier, physically blocking water molecules from getting to that polar head. And that's exactly why solubility drops off a cliff as the molecules get bigger.
So what's the big takeaway here? It means we can use this knowledge of intermolecular forces not just to explain properties, but to actually predict them. We can look at a molecule structure and figure out how it's going to behave. Let's test this out with a real example. On the screen, you've got 4 different compounds. Now, based on everything we've just learned about that boiling point hierarchy, can you put them in order from the lowest boiling point to the highest? Go ahead, take a second to think about it.
So did you get it? Let's walk through the 3 steps. First, we check if the masses are comparable, and yep, they are. Second, we figure out the main intramolecular force for each one. The alkane has the weakest van der Waals forces. The aldehyde has stronger dipole-dipole interactions, and the alcohol has the strongest of all, those hydrogen bonds. So finally, we just arrange them from weakest force to strongest, and boom,
That gives us the correct order of increasing boiling points.
Wow, we have covered a ton of ground, from tiny dipoles all the way to large-scale properties. So let's wrap this all up with a nice, clear summary of the key rules you really need to remember.
This slide really boils it all down to our two main principles. First up is the size trend. As the molecules get bigger, they go from a gas to a solid, their scent gets more fragrant, and their water solubility plummets. Second is the boiling point rule, and this is for molecules of similar mass. The boiling point always increases in this exact order: alkane, then ether, then aldehyde or ketone, and finally alcohol at the top.
Okay, to really lock this knowledge in, here's one final challenge for you. Apply that boiling point rule and rank these compounds. The answer is right there in their structure. It's just a great reminder that in chemistry, it's the smallest details that create the entire world we experience. Thanks for joining us on The Explainer.